Okay, what I wanted to give you an overview from today is an overview of the WaterSENSE project that I'm involved in, which is around making sense of the water value chain in Australia. And mainly what I want to talk about is just the overview of the current progress and opportunities, because this project is currently in progress, and the opportunities there for uncertainty quantification. So this project is maybe slightly different from others that you're used to. This is a project funded by the European Union through the under the Horizon 2020 space program, which particularly focuses on trying to get different partners to use the Copernicus satellite data. And under that program, Australia can be a partner because Australia signed up with the Copernicus data consortium, and as such we can apply, we could be part of a program. So it's a research-driven SME, small to medium enterprise consortium in this case. The coordinator and the technical partner is actually eLeaf in the Netherlands, so they are the coordinator. They're a small medium enterprise. Then there is Hydrologic Research, which is actually really about a platform, delivery platform. There's Water Technology, which is a partner in Australia, a small to medium enterprise. Again, they're a consultancy company. Of course, we are the only research partner here. And then there is a group in Germany which particularly focuses on rainfall research. eLeaf particularly focuses on evapotranspiration. Then there's Hidromod in Portugal, which is particularly focusing on hydrological modeling. And they're a spin-off from a university as well, so they're another partner. And then we have got HCP International Netherlands, which is like a one-man band. It's a small to medium enterprise, but it's basically only one person who delivers, particularly is focused on the communication component. Okay, so the concept of WaterSENSE is that we would deliver a WaterSENSE toolbox, essentially, which is a water monitoring systems toolkit. So it's supposed to be modular, it needs to be operational, it's a water monitoring system, and it integrates this Copernicus satellite observation data. But we also want to include things like groundwater and made-up models and in-situ data. The whole idea is that it's a toolbox which makes these algorithms and services available to users. And we then use the various apps which then provide the reliable and the actual research information to the actual user. Now, of course, from the University of Sydney, we're mainly focused on this end. We're not actually focused on the actual application, which is more what hydrologic research, Hydrologic does. It's one of the partners. So the challenges that we're trying to deal with is that the central idea is that we want to make sure that we can do water accounting, and we want to do water accounting, and we want to use that to try and capture, using satellite data, the water balance of a landscape element, and then to use that to kind of estimate the water use. For example, we might look at a subcatchment, a farm, or a river reach, and we want to link this to the scale of the observations and the output and the grid size. So if we have actually a certain size observations, we want to be able to then also be able to predict at that size. So, and particularly we want to try and refine that. And so the question is, how do we refine inputs basically through satellite observations, and how do we use the Sentinel, particularly the Sentinel Copernicus data, to try and refine those inputs? And then what elements do we need to actually quantify that? So, and that really depends, if we want to do this water balance and the water use, we really need to depend on what landscape element, and again, what grid size we're looking at. For example, we've been working on looking at quantifying irrigation reservoirs for a farm scale water balance, but we're also looking at, say, irrigation water use from fields. And then the next problem that we're really interested in, because we're a small to medium enterprise consortium, apart from the University of Sydney, is can it be operationalized to be able to do real-time predictions or forecasts? And so what is then what is then the desired accuracy and the scale that the user actually wants? So what kind of operational forecast or real-time prediction do we actually want to make? And how do we create then confidence in this real-time prediction and forecast that actually is accurate? And what data do we actually have available to validate that? So this is how we come to these research elements which is the current is what we're currently looking at. So the current focus list is looking at rainfall radar enhanced rainfall observations. So basically, we're looking at 1 kilometer square grids in real time for Australia. We're trying to come up with accurate estimates of real-time evapotranspiration down to about 10 meter pixels across Australia. We're trying to develop a way to predict accurate irrigation volumes down to also the 10 meter pixel scale. We also want to look at accurate volumes of floods and volumes, so floods in the landscape, but also volumes in farm dams and large reservoirs in real time down to about 10 meter pixels. We want to predict soil moisture in space and time and depth at near real time across Australia and at 10 meter pixels and at 2 depths, so down to about 60 centimeters. And then based on these improved ET and evapotranspiration and rainfall data, we want to estimate ungauged inflows in real time. And so essentially it's the ORAN model from the Bureau of Meteorology on steroids, but it also requires a real-time crop land cover map and accurate soil data.
So you might all notice this is the Australian water balance, landscape water balance, right? And this is a 5 kilometer grid system. And so you can have quite a bit of output for each of the different elements, but it's model based. So it is a model and you can zoom in down to say 5 kilometer grids and you can click on each grid and it gives you actually information on that grid, you know, what it actually tells you in terms of root zone moisture. So that's the kind of, you know, information that we're thinking about as well, but then we're thinking about it at much smaller scales and depending on what you look at. So it also requires a real-time crop land cover map and accurate soil data, which we'll talk about later a bit more. So there's some challenges that we have and that we're trying to resolve. One is the licensing system. When you think about how water is actually being assigned to people who can use the water is quite complex. So it's very difficult to actually figure out which river pump relates to what license, and that is used to actually apply to what fields. And so there's quite a bit of, I'll show you how complex that is. We don't know what are irrigated and not irrigated fields in different years. We just know what are all the fields that have irrigation infrastructure. We don't actually know which fields are irrigated within a specific field, within a specific year. We don't know, of course, how remote sensing, or we know a little bit about how remote sensing data is related to actual water observations. So it's an inferred relationship between the actual satellite observations and the actual water that is in the landscape, right? It's not a direct relationship. Then, of course, the satellite data is very irregularly spaced in time. And so how do you get that to daily data, particularly if the autocorrelation within that data is quite weak? So how do you actually scale that? And then, of course, how do we scale from field to catchment and back? So we want to be able to zoom in and zoom out, essentially. And then finally, of course, which is what we're working on in Where's All the Water, how do we close that water balance? Because that's really difficult. And that's already, we know that even the department has a big difficulty in trying to close that actual water balance. There's large volumes of unaccounted water as it is. So I'm giving you kind of a quick overview of some of the work that ELIF is doing, because that's their work and they're not that, you know, it's published, it's based on an existing process, but it's not actually, I'm not involved in that work by myself. So that idea is that you can use basically an energy balance approach to kind of use satellite data and a whole bunch of other input data to run through a processing system, which gives you an estimate of actual ET and a reference ET. So the whole idea is you're looking at wet pixels and dry pixels within a actual satellite data, and you understand the wet pixel is basically where you have maximum evapotranspiration, and the dry pixel is where you have zero evapotranspiration, and then you scale the rest of the observations from the satellite between that, using and basically calculating that out and figuring out what the ET is. And then you can use that to kind of calculate the incremental ET that you would get from areas that are irrigated relative to areas that are not irrigated. So that's kind of the whole overall flow chart that they're looking at. but the underlying algorithm that they're using to do the actual evapotranspiration has been published before. It's based on the work that's done in the past by Bastiansen et al. And that's really the key reference in that. And that is actually solving what we call in hydrology the Penman-Monteith equation, basically inverting the energy balance to try and come up with what the latent heat is, and using the latent heat to come up with the actual evapotranspiration from that. So, you know, it is based on physical processes. It is based on the satellite data, but it is in the end also an inference. So you have to actually process each image by itself and be able to calibrate it and understand what the actual evapotranspiration is. So there is in itself, there's quite a bit of, I think, uncertainty within that actual analysis, and there are opportunities, I think, to do it out of. For people who are interested in that kind of work, you would have to look at some of those references to get a better idea of how the actual process works. So what we're then doing is we're trying to translate that observed ET to actual water use per field. And so the idea there is that you convert this pixel-based incremental evapotranspiration, you look at that in terms of whole fields, and then you want to account only for the pixels that are classified as irrigated agriculture. And that's part of the problem, is actually understanding what fields are irrigated agriculture, and that is another problem that we could solve using satellite, or we hope to solve using satellite data, and I'll talk about a little bit later. And then you want to convert that to actually units of volume, say cubic meters, liters, or megaliters. So you'll be able to actually figure out what the actual total water use is. So then hopefully we will be able to calibrate that using metered water, people that actually have done measurements. And that in itself is, of course, a real challenge, because irrigators are not that keen to actually give you the data related to water meters. And so if we actually want to get to this in detail, there's a bit of discussion going on, and a bit of negotiation with actual people who actually have that data. And that's a long and arduous process, I might say. And again, we want to have a partner, of course, that has a lot of data, rather than a partner who has very little data. And it's interesting that so the government actually doesn't have a lot of that data. They're guessing just as much as we are. So just to show you, and this is the real first challenge, and that really, I was hoping that maybe someone has a solution around this, because this is something we're having a solution. We use a certain solution now, but I don't think it's the most elegant way of doing it. So the problem is that the relationship between the actual water that's being applied on the fields, the water that's being pumped from the river, and the actual relationship with the actual licenses is a multi-to-multi relationship. So each license can have several work authorities, where each work authority is actually a field that can be irrigated. And then each work authority can be linked to multiple extraction points, but an extraction point can also be linked to multiple access licenses. So, and multiple work authorities. So it's a many-to-many relationship that we're trying to then disentangle, and attribute certain amounts of water to certain amounts of fields that are actually being applied that come from certain abstraction points. So the way we currently approach it, which is what DPIE, New South Wales DPIE will work with themselves, that actually suggested that they do, is they basically cluster everything. So they basically develop a clustering algorithm to kind of cluster this and say, oh, well, this cluster is all related to this. And so we can then use that to try and come up with the water. That's, of course, not as clean as what we really wanted, is to bring it down to the actual field. And that's really what we have, of course, we would hope. We would hope to be able to say that field is getting this much water. And that's another complexity that we haven't really solved yet, in terms of, really we're just dealing with it in terms of these clusters, and also only you dealing with the surface water clusters. It becomes even further complexity when it involves also groundwater licenses. So yeah, it's not an easily disentangled system. Okay, the second challenge that we're trying to solve is which fields are actually being irrigated in real time. So the official supplied masks that we get from the government only are retrospective. So they talk about what happened last year, and they generally tend to only cover the potentially irrigated fields. So they show you all the fields that actually have irrigation infrastructure, but they don't necessarily show you the fields that are actually being irrigated. And so the approach that eLeaf uses in the Netherlands is they can do that by actually understanding your groundwater levels. They can figure out, they can look at its separate ET signatures, and then because they know where the groundwater is shallow, they can figure out which fields are actually being irrigated, which fields are not being irrigated, because they know where the groundwater is shallow. We can't do that in Australia because we actually don't have continuous groundwater level information across the landscape. So that's another question that we probably need to solve, is a question that we're trying to think about, is how do we actually solve that problem of having actually the understanding of where all the groundwater is and which fields might be actually using groundwater or sucking up groundwater through their roots relative then to those ones that actually, so which ones are groundwater dependent and which ones are not groundwater dependent. So there's a bit of work on that. The other approach that we're taking is a student, PhD student from Dahi, from Tom Bishop, who is also on the project. And so what he's done, he's basically trained in a machine learning model. Basically, as I always explain, we are users of data science. We're appliers of data science. We pluck something from the shelf and we throw it at some data. In this case, he trained it based, we've got SADA crop data, which is a very nice, is a fairly nice data set. Let's see if I can pull that up. Which you can get access to for each, basically, let me see, where's the summer crop? This one. Yeah, you can see it actually shows in quite a bit of detail different crops in different fields, so you can use that. So what we did in this case, we basically trained a model based on that data that we have, and we have about 20 years of data for that. And so we can actually train the model to try and identify from the satellite data different fields that have different crops. Now, some of that works well, some of that we can't. So there's certain crops we can see quite well. So we can distinguish quite well, for example, cotton from sorghum, because they have very different signatures. But for example, it's very difficult to separate wheat from barley because they're basically both a cereal and they're very hard to distinguish how they're different. Right, so that's some of the work that we're doing. The problem with that one too is that we still only can do that at the moment retrospectively, and we can't yet do this in real time. So it's how do we throughout the season look at those differences between the remote sensing signatures, and can we use that then to kind of come up with a probability of what we think is a crop, a certain crop. Okay, so that's some of the work that's going on in terms of those problems. Then, of course, Richard has worked with us on the actual estimation of water volumes in reservoirs using satellite data. So that's some of the work we've been doing. Essentially, it's a fairly simple approach. You can, from the satellite data, it's quite simple to actually identify using a water index, quite simple to actually identify certain, the reservoirs itself. We then go through basically a screening method where we say, well, the water has to, they have to be full at least 20% of the time. We do need a fine scale DEM, so we need a digital elevation model that's a 1 meter digital elevation model. And we can use that then to kind of understand what the relationship is between the water volume and the actual area of the reservoir. The reservoir also needs to be empty when we get the digital elevation model. And I'll talk about those in a little bit. And then we can kind of derive from that, we can run, an analysis, and we can actually figure, we basically assume a simple relationship. So the difficulty is not between the wet pixels and the dry pixels. They're easy to pick up. The difficulty is in the edges, because these are 10-meter pixels, and we want to know in the edge, at the edge, we want to know where actually is the water. All right, is it on one boundary of the 10 meters, or is it on the other boundary? Is it in the middle? So what we did with Richard, we basically came up with a linear relation, did a simple linear relationship between the water index and actually how wet the pixel is. And then we can use that to kind of derive this. We can then estimate basically the edges of the water, including the uncertainty, and we can then derive, basically an estimate of the volume relative over time, where we can show how full the reservoirs are, including an uncertainty and confidence interval. So I was pretty happy with that. I was quite excited about that work. So thanks to Richard, that really helped a lot in trying to get our head around it. So that was my first understanding of how this works. Anyway, there are some limitations, of course. We need a 1 meter LiDAR, a 1 meter DEM using LiDAR. Otherwise, the uncertainty really increases if it gets more coarse, because you're just looking at bigger. You can't find that relationship between the area and the volume. The reservoirs need to be empty when the LiDAR is flown, because otherwise we can't see the bottom of the reservoir. And the actual validation data in reservoirs is really, really hard to get. So we need friendly irrigators to help. So that's a real limitation. We actually don't have any real validation. At the moment, the only thing we can do is a validation on very big reservoirs, say the Minindi Lakes. We need to have enough cloud-free satellite images, because if there's lots of clouds, then also we can't, of course, see the water. And we don't know what the assumption of like 20% water occurrence for an active reservoir is actually correct. So there's a couple of things we still need to work on. And so then the challenge is, how do we extend that idea? How can we extend that to looking at DEMs, but to core scale DEMs, but also we want to look at floods in rivers. So not only do we want to know the volume in the actual reservoirs, we also want to know the volume in actual rivers. And of course, that water is moving. So there's a couple of additional assumptions that you have to make. So I've got a MPhil student working on these floods. So what she's doing, she's using basically the river gauge data and doing some modeling, some hydraulic modeling to try and use that as validation. The problem with that is, of course, that there's gauge data and head cross modeling. They both have their own uncertainty. So we're introducing uncertainty on top of the uncertainty of identifying the edges of the water on the satellite data. And then meanwhile, Ignacio, Richard, I have been trying to solve the problem of how we generalize this farm reservoir area volume curve. And that's quite difficult too, because we really have very limited observed data. So we've been trying to figure out how we might either get more observed data or how we might generate synthetic data to be able to actually figure out how we derive that we want a generalized relationship between area and volume. And so we can then apply that to these larger core scale DEMs. That's kind of what we're trying to dig out at the moment as well. All right, so the other thing that Ignacio has been working on for me on this project, and that's I'm quite excited about too, and also relates to the area of data science, is to try and look at predictions of soil moisture. So there are several products already that predict soil moisture directly from the satellite data. They mostly use the microwave, infrared, and visible bands, so there's basically quite a range of the different bands, but they mostly work at very, very large scales and only for surface soil moisture. So they look like, for example, some of these products work at 40 square kilometer scales. And so if you're starting to say, what's actually happening within my field, that really doesn't work very well. So it's not very accurate. And also some of the validation data, if you're looking at it, is not very accurate either. It's not very good. So the approach we thought we'd take is to actually use an existing soil moisture product, what is already, people have already published, in this case, SMAP, and trying to downscale that one using other, layers that we can have. And so they're using machine learning. There's a multi-layer perceptron model that he's using to try and develop the downscaling. And the idea is that we should be able to use different numbers of layers. Whether we use the surface model, we're looking just at the surface, we're looking at subsurface, because we also have different validation data for different layers. And the inputs include things like soil information, land use, sentinel, satellite, microwave data, SMAP motors, and surface reflectance and things like that. So there's a whole range of different things that we're putting in. The inputs are not random. It's not like we went, oh, let's pull whatever's off the shelf. So we basically did that based on the past literature, and people have saying these should have a relationship with soil moisture, and there are existing known relationships. And we use those kind of to feed them into this machine learning model. What we did, and this is one of the discussions we had quite a lot, was to do leave one out cross-validation. But what we actually want to leave one out is leave one location out. So we have several locations where we've measured soil moisture. We want to leave one location out rather than leaving out data points randomly out of the total data set. The other validation that we still need to do is a forward validation. So basically we predict only on 70% in the time of the data series, and then we want to predict forward the next 30%, because that will be a more stringent test of actually figuring out whether the model actually works.
Now, so can we ask a question now?
Yeah, sure, go for it, Robert.
Yes, so if you leave a location out, and if that location has parameters related to that location, then it's hard to do reasonable cross-validation, because just think of observations on cities of people, and you've got multiple observations on a person, but if you leave that, but you also have, you might have an idiosyncratic.
Yeah. No, I agree. That is, but that's the reason why if we do it if we do that as a cross validation, so we constantly leave one out and then look at the overall validation.
Yeah, but if you're leaving a whole location out, it makes it very difficult.
Yes, no, I agree. But I actually wanted that test. I wanted that more stringent test than leaving points out, because otherwise I think you're overestimating your accuracy otherwise.
No, but because it's not a stringent test if you can't do it.
No, I agree with that. But
now as for leaving 30% out, if you wanna, it depends what you want to do. Do you want to predict one step ahead or two steps ahead? Because the way to do it would be to estimate everything to a certain point.
Yep.
Take a window of 150 points and then forecast the next one, re-estimate using the next one or a fixed window. So leave the first one out, take the next one in, and then forecast the next one, and so on.
Yeah.
And similarly, if you want to use two-step ahead, so that leaving, so that's called time series cross-validation. If you want to just leave a whole lot out, I'm not sure. Well, that's different again.
Yeah, no, I agree. It would be the step ahead. That's really what we're hoping to build in. So to be able to do the couple of steps ahead, because also if we're thinking about this operationalized and real time, then that's what we want. We want to be able to predict a couple of steps ahead. But it's trying to make sure that we actually don't. So I'm worried, if because we were getting that's the problem, when you do this simple cross-validation where you just leave some part of the data out and not think about where you leave the data out. With these spatial models, you can often get, validation statistics of 0.98 or, R-squareds of 0.98. Or a Pearson's correlation coefficient 0.98. So I think you're partly tweaking it there but you'll see in the results actually exactly what you've commented on. I'll show you in the results, and I think this might be part of the reason that's something we probably should look at more closely. It might be something that you can help us with as well. So one of the problems we're having that the observed data has got some issues. The data quality itself. So what we have, and exactly as you were pointing out, is we have the performance is generally good, but there are some spatial locations where the performance is poor, which is exactly what I think you're pointing at. And that might be something that we probably need to investigate a bit further. I was asking Ignacio to try and work out, so what's specific about those locations that are doing poor, and that we need to try and figure that out. So in general, you get reasonably good correlations, you know, up near 0.8, 0.6, but you know, for some, there's quite a bit of a tail, and for some, there's really poor correlations in terms of the actual performance. And so when you look at it in space, you'll see that there are certain locations which actually do quite poorly relative to others. But in general, we're doing okay. These are some of the results. And you can see in general, we're doing okay in terms of predictions. The gray data in the background is actually that aura model that I showed you before, and the predictions of the aura model, which is much worse than what we're doing. So I'm pretty happy with that part of it, that we're actually doing better than some of that lens. So that's a land surface model at 5 kilometer grids, and we're clearly beating that in terms of our performance. So that's okay. But you can also see there's some issues with some of them, and definitely, you know, in terms of the correlation, some of the correlations are quite weak, and that's exactly, I think, what you're pointing at, Robert. That might be some of the problems that we're having. Of course, the nice thing about these machine learning models now is that you can actually pull out what are the actually biggest predictors on your actual model, what actually layers are most important in terms of trying to understand what actually determines the soil moisture predictions at each location. And I think that will really help us better understand what actually is going on, rather than just going, oh, we're just putting in a few layers. You really want to know what actually is happening for either the surface or subsurface modeling, where actually are the biggest, what layers are the most important. So, you know, things like clay content or the subsurface SMAP model, or the land use, you know, are different from, say, things like MODIS or whatever you're putting in, or rainfall. So that was kind of interesting. This is just a little snapshot that we're just showing one location where we're looking at a wet period and a couple of dry periods, and you can see a nice transition from wet to dry. Wet to dry in terms of the soil moisture, but you can also see, and of course, because it's a machine learning model, it also gives you some level of uncertainty analysis, quantification. So that's kind of useful to kind of portray, at least indicate how well we're doing. But you can see when it gets wetter, the uncertainty increases as well. So that might be another thing that we need to look at, is why does it increase the uncertainty when it's wetter? Is that the right way? And is that what we would expect? Right, so there's a couple of limitations. The quality of the Australian digital soil map is actually quite poor. It's good at the landscape level, but it's quite poor when you go down to a local level. So there's some work by Si Yang, who works also with Tom Bishop, where she's particularly looked at, you know, what actually is the accuracy of that digital soil map when you start drilling down and starting looking at specific points. And you wouldn't expect that because you're looking at a whole Australia map, but it can be important then to kind of understand what the local uncertainty is. Of course, the observed data is a real issue. Most of the soil moisture data is collected with what actually are uncalibrated probes, and they're good to map the time series trends, but they become then quite poor in absolute values. So actually figuring out the absolute value can be quite a tricky thing. We, of course, have also very limited spatial and temporal. If you go back here, you can see the spatial coverage of the actual data set is quite poor across Australia. There's huge gaps of where we have absolutely no data and no idea what actually is going on. So you're hoping that the data is representative enough for the rest of for the whole of Australia. And of course, that's purely a guess. So we're kind of thinking, what are maybe proxies for soil moisture that we could use to try and get to trends in soil moisture, rather than actually looking at real soil moisture data, because that's so limited. And yeah, the relevance of the satellite data is affected by the land cover. So, you know, when you've got trees and shrubs, then actually looking at soil moisture is much more difficult than when you've got grass or crops. Then you can see that much easier. Some other research from another partner. So this is about the radar rainfall interpolation. I find this really interesting too, although, you know, again, I have a less grip on that because it's one of the commercial partners doing this. So they've looked at interpolating the actual radar data from BOM and to transform that into a 5 minutes, 1 kilometer rainfall data set. They only have that for kind of short bursts in time. The plan is to have an extension to Australia wide, but we need to use something else like a satellite precipitation product to actually try to extend that. And there's no uncertainty related to this, so I'm interested in, you know, things like that as well. But it's in itself, you know, if you look at where the radar coverage is in Australia, we're thinking, okay, we've got all this radar data. How do we actually translate that into, you know, good rainfall data is quite a question and quite difficult to capture, particularly also because the radars are not standard, so they're not all the same. It's just some radars different, you know, some radars are more radars than other radars. What do you call that? You know, something like that. So there's quite a bit of technical issues in terms of trying to, you know, use radar data to get a 5 minute interval rainfall product for Australia. That can be quite tricky. But if you're looking at rainfall intensity, then that can be really important. Okay, we also got a partner who does just standard hydrological modeling, and he does really basically is just doing a land surface model, but again, he can do it on a 10-minute scale, and he's looking at those kind of things. So that's kind of a different way of approaching the same thing. I'm speeding up a bit because I'm looking at the time. So what do I see as some links and opportunities? I think mapping of crops and land cover in real time and as a forecast and really as a probability-based approach is something that we're, you know, would be really interested in, because that's really one of the things, and also Tom Bishop and myself are really trying to work on. And so it's something that we can maybe, there's some collaboration possibility. Because so thinking about, okay, we need to know, because it's really important for hydrology, it's really important for a lot of the actual overall land modeling, when there's these changes in land use, how that affects the actual, you know, soil moisture balance, but also the overall ET balance and a lot of different things. So actually understanding what actually is happening and being able to make a forecast or real-time prediction of actual crops and land cover is quite important. Well, yeah. This clustering, declustering, you know, what's the probability that this field is irrigated from that river pump? That's really what I would like to know. And I have no idea how I would get to that. There still is, I guess there is possibly some opportunity to look at these land surface models, large scale models that make predictions. Is that maybe something we want to downscale to a local scale? And is that maybe an easier way of doing these kind of things, and maybe using something Sentinel rather than running your own model? So, you know, if the model is already being run, why can't we use this data and then try and link it back, you know, correct it for actually what's happening locally? So looking at what level of information is relevant and how good can you use that local information across continental scales. We really need more formal quantification of all uncertainty quantification of all water balance components. And that's where it really links to where's all the water. We're not doing a very good job at saying what the uncertainty is in all these different water balance components and how how that might affect what we actually estimate in terms of other elements and other downstream things. So ET. But it's really difficult because what actually is the observed data and how much observed data do we have in terms of actual evapotranspiration? We've got our flux towers, but again, they're very sparse across Australia. There's limited numbers of data sets. So really getting a good understanding, a way, maybe the tricky way to try and get this understanding of it might help, even if that is first at a local scale before we go to, say, a continental scale. And then rainfall, the same thing, you know, understanding actually what rainfall occurs at each location and what's the uncertainty of that rainfall occurring at that location. And some of the work that Sally's done in the past already is working on that. And that's kind of I think there's still opportunities there, particularly linking into shorter term and radar. And I think it's really important to know that also for environmental impact assessments and things like that. We actually need to know that kind of thing, because that feeds into how we understand what might happen in the future. Of course, there's also the standard stream flow runoff and the larger scale modeling and hydrology that you know can still benefit from much better and formal uncertainty quantification that's currently just isn't done enough, not on a normal day-to-day basis. So okay, and then of course in terms of what I'm doing currently, I'm actually interested in this time space modeling of soil moisture, because I think that's really important too in terms of what we actually want to do in terms of overall understanding of how the water balance happens in the landscape and with irrigation water and all those kind of things, and planning, and you know there's a whole lot of things there that soil moisture is a key variable, and there might be better, there's probably much better approaches than what we were doing in terms of the machine learning approach, but that's the tool we had available and we wanted to have a go at. And we want to be able to do forecasts as well as real-time prediction, which is linked to what Tom's doing right now with this Soil Water Now project with GRDC, with the Grains Research and Development Corporation. So again, that's a project that you know tries to make an estimate of what is the soil moisture at this time, and can we make a prediction into the future. But it really doesn't have much uncertainty. So you know, again, a good uncertainty quantification around that would be really interesting as well. Anyway, this is our little blurb slide in terms of the project. It's a WaterSENSE, the project. Brian Jackson at Water Technology is our Australian partner, and eLeaf is the international partner on that. So that's all I had, and hopefully left enough time for questions and discussion.